How can we bring that in phase? Then it will make it unstable. 180 degree phase shift total. Then if you make another 90 degree, then it will become a positive feedback. Already you have a 180 degree phase shift due to negative feedback, additional 90 degree coming from the output. I cannot add another 90 degree there. I have to get rid of that additional 90 degree actually. Correct. So how can we reduce that phase shift? Okay, let me. So this is your C out. Let me mark it. I'll call it C out. So we know this current is going IL, correct. So this voltage is 90 degree out of phase. So you guys remember RESR? What would happen now? What will the ripple? So this is your V out. So delta V out will be delta IL. This is delta IL actually. Only ripple component is going inside a capacitor. So delta IL RESR plus what is the other component? This is charge Q. How much was Q? This is Ts by 2 and this is so half into Ts by 2 into delta IL by 2, correct. And then Q equal to CV, C delta V naught. Q by C. Okay, so it makes it delta IL by 8 times of FSW C FSW, correct. Now if you break delta IL into V in minus V out by L and D times TSW, then you will get FSW square term, but for simplicity I am just writing in terms of delta IL. Okay, so this is in phase, this is 90 degree out of phase. Okay, and I am interested in phase, which means delta IL RESR should be much greater than delta IL over 8C FSW. Let us call it C out here. Okay. But how much more? Not dominating actually. The only thing is that, see, you may have a little phase shift, as long as your peaks are aligned, you are fine. Okay, you may have some non-linearity. I mean, if you keep increasing this RC actually, it will become more linear and linear. Let us say I keep increasing the R. If I keep increasing the R, then my delta IL RESR component will keep increasing. If I increase the C, then it will keep reducing the other component. So, both will have a same effect as such. Okay. So, it is a product of R and C which matters here. So, if I keep increasing product of R and C, your delta IL RESR component will start dominating over delta IL over 8C out FSW, which is 90 degree out of phase. Okay. So, you have to make sure that your RESR product in such a way that your peaks are aligned. Okay. And usually if your RESR C out is greater than D times TSW by 2 and 1 minus D times TSW by 2, then output is stable, which means delta V out is in phase with delta IL and V out is bounded. Okay. So, we need to meet both the conditions, D times TS W by 2 and 1 minus DS time, and if you want to cater to full range 0 to 100%, what does it mean? For D equal to 0 to 1, RESR should be greater than TSW by 2. And if you do your calculation, hand calculation, you will see your, this is a 0 actually. So, this will add a phase lead, and that phase lead is I think 70 degrees or so. Okay. So, out of 90 degrees, 70 degrees cancelled. So, you will be left, phase shift leftover will be 20 degrees or less. That is, keep increasing RC out, it will start approaching to 0. Okay. So, there is a derivation for that. So, what you need to do basically, you have to write the equation this in terms of T, okay, and then you would have to differentiate it to find the maxima of the output. So, the maxima of this V out, the maximum point of this if same as maximum point of the other component, which is, so the peak of this is aligned with the peak of the other, I mean you have two components, so both peaks are aligned. So, which means the maximum of that is should be same of same other, and you will get a condition for T, and then you will see that if you substitute that, then you will get TSW by 2. The derivation is given in my thesis. So, I will tell you where is the link and you can go and look at it. So, if you go to my page, so if you click here this link, it will take you to my thesis. You can download PDF from here. So, it is 13.6 MB. So, I will tell you where exactly it is. So, there is chapter 4 on hysteretic control. So, if you go to page number 44, this is the whole derivation, it starts from here. So, 4.1.1 section. Okay, so you have to write everything in the time domain and just keep following the how you, I mean you have a current, so what will be the voltage from there you can find and write the equation, and then you have to differentiate to get the peak and valley. Okay. So, maximum and minima can be, and that will give you the condition for T peak, and you substitute for T value is this, and you substitute in the original ripple equation, this is what you get actually. Okay, T off you get here, and so T off is nothing but 1 minus d, and for the other case, so this is your for peak, and for valley you get T on by 2, and T on by 2 is nothing but d times TSW. So, if you have to meet the entire range 0 to, so and this is what I have shown, if you want to meet only, if you meet only one condition when you are changing the duty cycle, then you may have a problem. Around 50% you should be okay, but when you go more than 50%, one will limit, other will not limit, and I have shown that condition here. See, this is limited, but other side is not limited, and when you have a d greater than 0.5, then so if I try to meet, let us say at 50% duty cycle, then this may happen at higher or lower duty cycle. So, one will be limited, but other won't. So, if you want to limit both sides, then you have to meet that condition TSW by 2. Okay. So, let us take an example now. So, if this is the condition, delta IL RESR is much greater than delta IL by 8C FSW, then we can ignore okay. So, what will happen, your delta V out will be delta IL into RESR. What is delta IL? V in d times 1 minus d by L. Okay. So, which means delta V out equal to V in what is delta V out here in this? Delta VH, huh? So, which means FSW equal to 1 over TSW, which becomes V in 1 minus T over into RES. So, this is your switching frequency, which is depending on your hysteretic window. This is delta VH. Okay. Your inductor value, your V in, and duty cycle also, RESR. So, it is a function of everything, if it looks like, and everything is can be changed except your delta VH. You can only control delta VH, rest of the thing is not your control, because V in may vary. If somebody is looking for variable output, then V out also may vary. So, let us say just take the case of your if output is varying. So, assume V in, delta VH, L and RESR are fixed, but V out is variable. This implies D is varying. Do you remember the ripple curve? Duty cycle versus delta V out. If you have a fixed input and output is varying, how does it look like? So, if this is your D going from 0 to 1, so it was symmetric around 0.5. This is your delta V. So, which means, and this is for FSW is fixed. Now, if I fix delta V out, I am forcing here delta V out to be delta VH. So, if this is FSW, what would happen to the switching frequency? Can anybody tell? Increase or decrease? Same, correct? Parabolic only? Huh? What? Triangle? How come triangle? It will be parabolic, huh? Same. It is proportional to D times into 1 minus D. Correct? So, if let us say at 0 and 1 it will be 0 because it will not be switching at all. Let us take the case 0.1. So, 0.1 into 0.9 which is 0.09, pretty close to again 10% duty cycle, and if you take the other case 90% duty cycle, then again same. Okay. So, which means whatever you had here, it will be roughly at 0.5, it will be 1/10 of that, okay, or it is a 0.09 actually. So, it is slightly more than that, but roughly you can say that. So, the peak, the maximum frequency will be at 0.5, then it will start reducing. So, it will have a same profile. So, which means as long as I am operating around 0.5, my frequency will not vary that much, but the moment I go to extreme duty cycles, my frequency will look very bad. So, this is only with the duty cycle. Now, assume your Vin is also varying. So, if Vin is increasing, then we know the ripple increases with that. So, your switching frequency is proportional to Vin here, correct, and inversely proportional to L and proportional to RESR. Okay. And from here you can intuitively look at, if let us say I increase the L, your ripple will reduce. When ripple will reduce, then the ripple which is seen by the comparator is less, and but it is, you are limiting the ripple at delta VH plus minus delta VH by 2. So, the only way to increase that amplitude is to reduce the frequency. If you are increasing the L, same thing happens with the RESR. If you are increasing the RESR, then the ripple will increase. Now, it has to reduce, the feedback has to reduce because you have to limit within that window. So, it has to increase the switching frequency in that case. Okay. Switching frequency is not constant. FSW is proportional to V in then what else, into D into 1 minus D into RESR, and it's inversely proportional to 1 over delta VH to L. So, once you have fixed the L and you know RESR, everything is fixed, now you can decide delta VH at what frequency you want to operate, but it will vary. RESR is also not fixed. Okay. So one way is like you use a very small RESR capacitor, 1 milliohm or so, and you in series you add a very like accurate resistor, RESR whatever you require. Okay, so let's say I want to design this. Let's see how, I mean how much RESR I will require. So let's say FSW equal to 1 megahertz at D equal to 0.5, correct. V in equal to 1.8 volt. I am choosing L equal to 1 microhenry and C equal to C out equal to 10 micro. Any other parameter? Okay. Delta VH equal to ripple, let's say I want 10 millivolt. Okay. So substitute here and we can find value of RESR, correct. One mega, which is 10 power 6 into how much was 10 power minus 3 into 10 power minus 6 over sorry RESR, that will go 10 power 6 multiplied by, this was 10 milli, yeah I think it is 10 power minus 3, 10 power minus 2 into L is 10, okay, divide by 1.8 into 0.5, 1 minus 0.5, how much is this? So this cancels out, so this is your 10 power minus 2 over 1.8 into this becomes 0.25. So 10 divided by how much is this? 0.45, pretty close to 20 milliohm. Correct. So now let's see if RESR meets that condition what we have, and we know that RESR into C out should be greater than TSW by 2. So how much is RESR? TSW by 2 is 500 nanosecond and RESR into C out equal to 20 into 10 power minus 3 into cap was 10 power minus 5. Okay, how much is this? 2 into 10 power minus 7, which is how much? 200 nanosecond, which is less than that. So this doesn't meet that condition, which means you have to increase either C out or RESR, and then your frequency will change. Okay, if I increase the C, but because my frequency is not depending on C here, okay, it may depend, but we are considering that that component is very small, the ripple due to cap only. So it may vary maybe 5-10%, but frequency will be a strong function of RESR here. Okay, so if you change the RESR, then it will change the frequency, but if I change the capacitor, then it may not affect your frequency much, or you change the delta VH to get the frequency back.